I'd like to welcome you to the critical design review for the Artic power system. Introducing the team, my name is Lisa Ferguson. I am the team lead and also in charge of the hardware design. We have Dee Moser at the end, who is in charge of documentation and administration. Dylan Schindler was in charge of the software development. Then we have Emily Davey and Austin Spurter for testing and verification. The agenda today will be going over the project background, the motivation behind the APS system, then into product specifications, some of the requirements put upon the APS project, then the hardware design approach, software development, the testing activities that were performed, and then a functionality review of the hardware that we have completed this semester and some of the testing that we have done. Then we'll have a brief conformity review and budget review, and then there will be time for questions at the end, so please hold your questions until then. And first up is Emily with the project background.
All right, good afternoon, everyone. I know it's a little late in the day, so try not to nod off. I'll try to scream at you to keep you awake. Contrary to some of the signage you might have read earlier, we are not an avionics team, and we are actually composed primarily of electronic engineers, computer engineers, and software engineers. I actually believe we are primarily electrical and software. So our project is quite interesting. What I'm going to talk about today is the system overview, the overall system block diagram, and the system operational breakdown. So what did our team accomplish this semester? What was our objective? So the Artic power system, what we did is we designed a power conditioner to be utilized in the Arctic Circle by the Coast Guard to power multispectral cameras. So these multispectral cameras will be primarily used for some type of surveillance in the Arctic, specifically for capsized boats, any Department of Defense issues we might have up there. But really the focus is creating this power source that they can use in such a region with such harsh climate. For the objective of our presentation, we are going to talk about the Arctic Circle. Hopefully you can see in this picture here. We're going to talk, most of our climate data actually came from Barrow, Alaska. So that coastal northern region of Alaska. This is an overall system block diagram of the APS. I'm not too particular about you reading into this too heavily because the next slide is going to go into detail. What I do want to draw your attention to is that there's 3 power inputs and 2 power outputs. There is only one line here shown for the output, and that's because it's a 20-watt combined source. What's really important about the APS is since it's going to be in such a remote location, it has to be able to be maintained by a standard operator. So you will see a dual arrow here for maintenance for the APS. Specifics. Let's talk about what the system actually has to accomplish. It's going to take the 3 power inputs separately. AC power to include US and European power, as well as wind and turbine. So literally you can plug our system into any standard wall, not only for testing, but for actual implementation if need be. We also take a solar panel rated to 20 watts and a hydrogen fuel cell. The 2 power outputs that we are expecting from our system is a 5-volt line and a 12-volt line. These are specifically designed for the multispectral cameras that we are anticipating from the Coast Guard and the Alaska Center of Excellence. However, the system could be diversified in the future to power other systems. The primary control of the system will happen through a microcontroller, which will control event logging, system monitoring, and power switch control. This is what we would think the APS would look like after its final development. So you see the 3 power inputs. We have to have some type of outer casing to protect the electronics from the harsh climate in which you would see in the Arctic. We don't want any of our components to freeze or have water damage, so it would have to be in some type of environmental casing, and then the output to the cameras. So let's get into those specifics. What are we looking at from a hardware-software perspective? So in order to address those, we're going to talk about a functional design specification, product requirements, and the functional software design specification. So a detailed specification is really what our team used to scope our project to a semester. So what we wanted to do is focus on the internal electronics. So that means that we had to omit certain things from our project. But first, let's talk about what's inclusive. What did our team accomplish or work towards this semester? Primarily what we wanted to do is create 3 separate lines from the input source to the output source. And some of the hardware between we will address later. However, we wanted to omit things that might have been a little difficult to implement with our time constraints, to include the system housing or that environmental casing I talked about earlier, and also any internal temperature regulation. So the interior of the box, we actually designed all of our hardware to have an ambient temperature of 0 degrees Celsius. So in order to maintain that temperature, it is a constraint we put on the housing and not on our system. The product requirements. Our hardware, we're expecting to fit within a 50 centimeter cubic space with about 10 kilograms of weight. For all of you that might be unfamiliar with kilograms, it's about 22 pounds approximately. We're looking for those 3 input power sources, and then what are we going to do with the software? How are we going to run our system? We're going to use event logging, data persistence, and data output. The data output is primarily for the maintainer so that they know if the system has voltage spikes, if water got into the housing, things like that. The data persistence is important because what it talks about in data persistence is if the system is power cycled, so if it's turned on and off again for any reason, we want to make sure that we have access to that data after the off-on again. So for all of you in the back, this diagram is probably a little bit of an eyesore. There's nothing too technically difficult here. This is just how we broke our system into subsystems. So try not to get too lost in all the boxes and the arrows. I will walk you through a little bit of it though. This here are the input sources, and over here you will see the 5 volt and the 12 volt output. The center piece here where all of them come together is actually a bank of supercapacitors. Since the climate in the Arctic is so cold, we cannot use batteries of any type. So in order to prolong our distance between maintenance, we were actually hoping for a maintenance span of about a year, so you could leave it out there for a year and then come back. We actually decided to use supercapacitors very similar to what you would see in a space system. Otherwise, everything between here and here is some type of power regulation and voltage and current measurement to ensure that we are providing what we said to the system. For a more in-depth explanation of our hardware, I'd like to pass it off to Lisa Ferguson.
Thank you, Lynn. So I will be going into the hardware development process for the Artic power system. A agenda of what I'll be covering today. So first, the design approach, how we went about designing this system, any of the critical design decisions that sort of molded our project, and then design dependencies, developmental process, so how did we actually go about going from an idea to physical hardware, and then a functionality analysis where we got in this semester with functional hardware, and then an overview, robustness, reliability, and a little bit about the system efficiency as well. So first, the design approach. As Emily showed you that block diagram, we took the inputs, outputs, and control. Those were our 3 main sections that we dealt with. Each of those sections were then further broken down, as you saw in the boxes. Those were the unit subsystems. So those were the load switches, the sensors, and the power supply. Those each were part of a subsystem, so whether it be the solar panel input or the 12 volt output, something along those lines. So we developed each of those unit subsystems individually to ensure functionality before upscaling it to the entire subsystem. So then we decided to prototype one input to output path first. So we went from the hydrogen fuel cell all the way through to the 12 volt output. Now the hydrogen fuel cell and the 12 volt output were selected for specific reasons. The hydrogen fuel cell because it was the only boost architecture used in our system. Then the 12 volt output was a buck boost architecture power regulator. It was chosen because the buck boost architecture that was used is implemented in 3 other locations throughout the power supply. So proving functionality with the 12 volt output, which had the lowest operating current, so we felt safest testing that and working with it, would allow for proof of concept of the rest of the system, as the only changes between that and, say, the 5 volt output were just resistor and inductor values. Oh, yes, okay. So the critical design decisions. We decided to do our development on in-house proto-PCBs. So these were printed circuit boards milled here on campus. They are unmasked, unsilked, and for those of you that aren't familiar working with those, it's basically raw copper. So it becomes a little bit more of a challenge when you're actually fabricating because there is a cleaning process where you have to go through and ensure that there aren't any shorts in the boards before you start working. The initial testing then was done on a PCB because our entire design was very surface mount component based. So in order to breadboard that as you would a traditional electronic system, you would have to put them all into breakouts and then put them onto breadboards. So it was much more time efficient for us to go straight to the PCB, which is a printed circuit board. Sorry about that. We then decided to also develop our own microcontroller board. We did use a Launchpad that you'll hear about a little bit later from Dylan for the software development, so we could develop hardware and software in parallel, but we did develop our own microcontroller board and power for that as well. And then we decided to go with a supercapacitor in the system to store energy and provide time for the microcontroller to react should anything catastrophic happen on the input or the output. And if there was a catastrophic power failure, we would have time to properly shut the system down. All right, so there were two major design dependencies in the hardware development of the Artic power system. First was the use of TI Webbench. TI Webbench is a Texas Instrument software suite specifically for developing power supplies. So you can specify the expected input power range, the output power range, and then you can actually, it will populate a series of potential solutions that you can then further tune and change to meet your needs better. So by using the TI Webbench, we were able to very early on develop the power supply architectures that we were using, which was fantastic since we were definitely running short on time this semester. We were able to then optimize the designs for efficiency, so we had the most efficient power supplies that were available from TI, which was very useful because we have such an expected a lifespan of a year of operation. The system must be incredibly efficient with handling the power that it's given because it will be very limited. The downside of using the TI Webbench software is the designs are extremely reliant upon Texas Instrument products. One instance we ran into was with the Boost architecture. It used a non-Gullwing Boost chip package, which was meant for a production implementation with a solder reflow oven that we did not use. So soldering that by hand with a soldering iron more than likely caused heat damage and shorting the chip, so we were not able to prove functionality of the Boost architecture. The other design dependency was the use of the DipTrace software package for schematic and board layouts. This was mainly because that is the software package I am most familiar with, and we did have an academic license available. However, there was a pin limit for our schematics. We could only have 500 connections per schematic sheet, and with a large system like that, we met the 500 pin limit with just the microcontroller board. So we were not able to create a single input to output schematic for the entire APS system. However, had we used a similar project like Eagle, that is actually surface area limited, so we would not have been able to populate the boards. So there was drawbacks with both projects. So the hardware development process, as I stated earlier, we were first divided into subsystems. We figured get the smallest unit possibly working, and then build up from there and iterate and combine the systems as we got hardware functionality developed. Once we broke it into the subsystems, we then developed the schematics, created the board layout and proto-PCBs and populated those, and then began bench testing. Once we had the functionality of the unit subsystem boards working, any of the changes, fly wires, removing components, changing components, things like that, those changes were reflected in the next round of schematics, and the process was iterated, and the unit subsystem boards were combined until we have the system we're at now, which has the main power architecture and the sensors combined into a single printed circuit board. However, due to time constraints, they were not able to be entirely completed. They are populated with components, however, the vias were not able to be sewn in yet. And then we did subsystem testing. So just to walk you through the process that I followed, this is a schematic of the buck boost converter for the 12-volt output. This was one of the boards that we have functioning in King Lab right now. So starting with this schematic, this was a suggestion from Texas Instrument. We did change it a little bit, get components that were more available to us. From that schematic, it goes to a subsystem schematic. So this one here, you see that same power architecture. And then we have a load switch here, a current and voltage measurement circuit here, and then an output crowbar circuit here that prevents overvoltage. Now taking that, this is a board layout of the first schematic shown. So this is just the 12-volt output. You can see most of the circuitry up here. All the things you see in black would be copper when printed on our mill here. That is because of the high currents that these boards will experience, and it was a safety factor and a suggestion from Texas Instruments. This is that same schematic, or same board layout shown without the copper cores, just so you can see the connectivity. However, these traces would not be shown on the final board, and it would definitely look more like this. Now this is the subsystem board. It's just turned on its side just so it's not so small. And then you can see here the crowbar circuit here, the voltage and current sensor there, and the load switch up here. That's all been integrated into a single board. The final layout of this will look quite some of this with the individual subsystems modularized and connected to a master control board with the microcontroller. So a functionality analysis, as I mentioned earlier, the buck boost architecture for the 12-volt output is functional. We use this as a proof of concept of functionality for the other buck boost architectures in the APS system. The boost architecture, again, is not functional. This is more than likely due to a population and fabrication error, not necessarily to the design. Load switches are functional and integrated with the microcontroller and the voltage and current measurement circuit. We have the voltage portion of it functional and integrated with the microcontroller as well. And we have tested and verified the supercapacitor, which you'll hear about a little bit later. For robustness and reliability, these values here, we decided to use an off-the-shelf AC-DC converter for their AC wall input. So this value here, the 82%, that is a very standard off-the-shelf value for efficiency for an AC-DC converter. However, these boost and buck boost converters that you see here, we were able to optimize for the most efficiency we could get. So this value here, the 94.5 efficiency, is very good for buck boost converters. The shock and vibration, I wanted to bring this up because we did not have a chance to test shock and vibration. However, it was considered in the design. So by using surface mount components and making sure to firmly secure any through-hole components, it was taken as a consideration, as these will be probably in a very rugged environment and could very likely be experienced to shock and vibration. So some future development, as I was saying, use a solder reflow oven to populate the boost converter. This would hopefully remove any errors caused by hand soldering the particular boost chip component. Combining the subsystems into a master board, that would be the next revision once we prove functionality of the individual power sources. And then integrate the internal components in the actual housing. So as Emily was talking about earlier, getting the weatherproof housing built that has all the necessary insulation and actually integrating that with the electronics and potentially adding some active heaters as well. And then due to time constraints, we'd love to be able to do some long-term thermal testing and long-term Arctic environment testing as well, but we're not able to accomplish that this semester. Next, I will hand this off to Dylan, who will go into the software development process.
So today I'm going to be going over the design approach that I took with the software and critical design decisions that I made, the overall development process that I took throughout the semester, some of the design dependencies, functionality analysis, so what is working with the software and what still needs some work, and then finally the robustness and reliability. So for the design approach this semester that I took with the software, I tried to move towards an interrupt-driven architecture, which means there's one peripheral, so an analog to digital converter or an analog comparator tied to each system function. System function being one of those blocks you saw earlier in the block diagram. Then all system responses take place within these interrupts to the processor. There's a library of functions that are then called throughout these interrupt service routines. An alternative approach that I considered but ultimately didn't take was constantly polling each peripheral throughout the system, and then multiple system functions connected to the same peripheral. So this is the same system block diagram that you saw earlier. It just shows instead of the power lines going through the entire system, each of these little lines right here is where the microcontroller actually connects to the system block. Either communicates it with either commands that system block or gets data from it somehow. So for the first critical design decision that I made was the microcontroller unit, or MCU. I chose the Texas Instruments Delfino. One of the first reasons is it has a Launchpad, which is sort of a proto board that you can work on. So this allows for rapid prototyping with the software, working with Windows, and then downloading directly through USB. It also has 8 window comparators, which were really useful when working with voltage and current measurement systems, when dealing with voltage spikes, current spikes, that kind of thing. Also, it has configurable peripheral interrupts. That means every peripheral, being the ADC or analog to digital converters, each one of those can register its own interrupt to the CPU, so then it starts servicing that. Next, I went into the critical design decision of the programming language. I went with the C programming language because the Delfino is a very, very low-level system. A lot of the code that I was writing was actually directly addressing registers within the CPU instead of using high-level functions like printf or something like that. Additionally, a lot of it was actually in assembly language, which is a very, very low form of programming. Also, the Delfino has no support for cumbersome runtime. So this means Java, Python, C++, anything like that can't actually run on the Delfino chip. And finally, C is natively supported. It's actually the only programming language supported, so it made my decision fairly easy. Next, I went with interrupts for the overall system. So interrupts allow for a much faster response for the system. So instead of polling and going through, let's say, a while loop and checking each system in a row, an interrupt will allow the system to immediately go and service whatever happened. So if there's a voltage spike, instead of waiting to get to that comparator, it it can immediately hit the load switch and help protect the system. And even though it's within the millisecond range, milliseconds really do count when you're dealing with a voltage spike. Also, it allows for less system resources used. So when you're doing polling, you have to have all peripherals turned on at all times. Whereas with interrupts, I can actually select and choose which peripherals are on and bring the power consumption of the microcontroller down, which is really important for the efficiency of the project. And then finally, the comparison logic is largely taken care of by the interrupts. By going through and enabling the interrupts and configuring them, I don't need 10 if statements nested within each other. Next is the software development process. Now, I committed to cardinal sin in software engineering, and I did not follow a top-down approach. I actually went with a bottom-up approach. This is normally not done within industry, but the reason I did this was because I have never worked with this chipset before, and then no one on campus has worked with it either. The only resource I had was a 2,500-page technical reference manual and some TI's example code. So in order to build the overall architecture, I had to go to the lowest level and figure out how to get those peripherals up and running. So for the approach I took, I first created the system initialization code that allowed me to actually flash code onto the chip. And then from there, I identified the necessary peripherals. Originally, it was only the ADCs and comparators, but then I also realized I need to add a little bit more into that. So I create the peripheral initialization code, run a few unit tests to make sure they're initialized correctly, and then move down to try to get those peripherals to actually match the desired functionality for the system. And then from there, run unit tests to make sure that that functionality matches up with what I need and what's within the specifications. And then from there, I'd integrate the peripherals with whatever had already been done, run some more tests, and iterate as necessary until I ran out of time this semester. And then finally, a full system test with all interrupts up and running to see if they communicate effectively and the system continues to run as expected. Some of the design dependencies with the software is extremely dependent on the TI-320 family of microprocessors. That's where the LPO comes from. Because the software is so low level, it's directly communicating with each register on the CPU. Moving over to a different chipset or anything like that, the software would have to be entirely redone. However, the software is configured to recompile every time the code is actually flashed to the Launchpad. So updates to the compiler, new versions, anything like that shouldn't have any impact on the software overall. So for a quick functionality analysis, these are the specifications that are met with the current revision of software. So first, the system date and time is loaded from the host system into the microcontroller. Currently, it's in a Julian calendar date and time, 24-hour time format. Specifications require Unix time, but just for simplicity's sake, when we're reading data off the micro, we kept it in a simple format. The event log creation, we are able to create event data. It's in a formatted or unformatted stream. However, it is output through a UART communication to a program called PuTTY running on the station, instead of being saved on the microcontroller. We have the boot up event running, so when the system comes alive, it just basically says I'm alive. System watchdog events, so every time, about every 30 seconds right now, it will log a message saying what input power sources are used and what are the voltage measured on each input power source. The voltage spike and the critical power loss events are also functioning with the software. The specifications that have yet to be met by the current revision are first, the data persistence and data processing. Right now, all events are actually output straight into the Windows host system. None of it is saved onto the flash memory of the actual chip. The program is initially saved into flash memory and then run from there, but none of the code is. And then finally, system data export. So right now, we're only exporting through a JTAG bridge, which is basically a debugging interface to the Windows host system, rather than outputting through the native USB pins and allowing for USB ports to be attached to the microcontroller. There's also 8 GPIO pins that can be configured with the system, just aren't configured as of yet. Critically humidity events, there's a humidity and temperature system or sensor within the system, and it uses I2C, a communication protocol, and currently that is not within the software. And finally, no load or current spike events. The current measurement system that we developed actually isn't quite functioning, so there's no real way for the software to test that out and make sure it's actually reading the correct current values. Now finally, for the robustness and reliability, the Delphino actually includes a watchdog timer, which is essentially something we have to check every now and then to make sure the system is still healthy, which is extremely important because a lot of the peripherals work by checking if a flag has been raised. So over time, if 10 seconds have passed and that flag has still not been raised, watchdog timer can go off and make sure the system can continue on with its next tasks and doesn't get hung up on that one peripheral. And finally, it includes error correction circuitry, or ECC, within both memory or RAM. So if there's any errors, it can hopefully correct those within a few. Now I'd like to pass it on to Austin for testing and verification.
Thank you, Dylan. Today I'll be covering the testing and verification that we have performed on our system. I'll be covering the testing methods and equipment used, go over some of the testing results, and then some of the omissions and difficulties we had while testing. So some of the methods and testing we did was conductivity test, make sure there's no shorts in the open circuits on the board, unit testing on each individual component, as well as subsystem integration tests with the microcontroller. Some of the equipment we used was the multimeter, both benchtop and handheld, the oscilloscopes, portable power supplies, and the thermal chamber we have in AXFAB. So the components that we had functioning as expected was the capacitor bank. We were able to put voltage into it, store energy, and then discharge that energy. Buck boost architecture, the 5 and 12 volt crowbars, the voltage sensor, and the load switch. And I'll go into each of those a little later. We also did environmental testing, so we used the thermal chamber in AXFAB and froze all of our boards down to 0 degrees Celsius for 15 minutes, and they were all still functioning after that test. Some of the omissions that we did not perform, testing down with one complete pipeline. Due to time constraints, we were unable to debug and able to connect one whole pipeline. The shock and vibration testing, the housing verification, and the long-term deployment testing were all omitted due to time constraints in one semester. Some of the difficulties, the current sensor, the chip we chose, we were running off the 3.3 volts provided by the microcontroller, and that ended up allowing the operational range to be within like 1/10 of a volt. So we were looking into supplying out the higher voltage, and we're unable to get that circuit completed. The microprocessor current limit, and then the surge protection on the inputs to protect the surges, we did not get those circuits working properly. So now I'll go into some of the functionality review of the boards. The input lines, the hydrogen, solar, and AC, the two outputs, the 5 and 12 volts, as well as the microcontroller, the sensors, and the load switch. So here's a layout of our whole system. You can see the three inputs of the AC, the solar, and the hydrogen inputs, our capacitor bank, and our 12 volt and 5 volt outputs, and then the 3 volt output to power the microcontroller board. So this is the solar input. We're expecting 3 to 20 volts on the input, and we have the output out here. So this is the voltage and current sensing circuit. This is our load switch, which allows voltage just to be passed, and then if a voltage spike occurs, the microcontroller is able to flip this switch so no voltage is passed to protect the rest of the circuits. And then we have our buck boost converter to provide the 12 volt regulated output. The hydrogen input is simply a boost converter because we're not expecting any more than 12 volts on the input. So we have the boost architecture and the output over here. The AC-DC converter is right here. We have the input from a wall plug, and so I'll take the mains power, AC power, and then output a 12 volt signal. We also have the current and voltage sensor here and the load switch there. 5 volt output is a buck boost converter as well. We have the load switch, the current and voltage sensor, as well as the crowbar circuit, which can be seen here. What the crowbar circuit does is prevents any over voltage. So like the load switch, but it is not connected to the microcontroller. It is simply, it has a resettable fuse in it. So if any over voltage does occur, it will cut off all the power to the cameras to protect the cameras. This will look exactly similar for the 12 volt. Again, you have all the same components, and you have a 12 volt crowbar circuit, so it allows up to 12 volts to pass and will cut off voltage above that. Here's the 3.3 volt buck boost converter. This will be simply used internally to power the microcontroller. And I would like to invite Dylan back up to talk about these next two.
So this is the microcontroller and the Launchpad. This is the Launchpad that I mentioned earlier for rapid prototyping. The JTAG bridge that I mentioned earlier, or the debug bridge essentially, is right here. And then this is the actual microcontroller board that we printed on campus, with this being the 176-pin chip that we're working with. The one on the Launchpad's 100-pin, but there's not too much difference between those two. And the headers right here go out to the various systems that was seen earlier on that diagram. And then this is a screen cap from Putty that Saucer mentioned earlier of a software demonstration. So it's hard to see, but the first line up there is the system coming alive and registering a boot up event saying, I'm here, I'm functional, and timestamps with each event. Then it goes through at 30-second intervals and includes which load switches are currently active or which inputs are being used. And then measurement voltages for each input. And currently these ones only have the AC input attached. And then right here is actually where the microcontroller experienced the voltage spike event. So an interrupt occurred, it flipped the load switch to prevent more voltage from coming in to back the system. The reason why there's multiple interrupts being logged right here and here is there's actually a noise range associated with the ADC. So when it hits a certain threshold, it fires off the interrupt and registers an event. However, there's enough noise where it's constantly going above and below that threshold until the voltage spike reaches a certain region, about 1 volt higher than the threshold limit. There are noise filtering and ways to compensate for this within the software that has just yet to be implemented. So it fires off the interrupts until it stabilizes itself, and then right here, and then again it starts going off the watchdog timer and just registering more and more events. Now I'd like to pass it off to G for the budget.
So over our 14-week semester, we had a $1,000 budget, and here is where the will break down. We'll go over the developmental budget first, and then the estimated prototype cost for the customer. So with our $1,000 budget this semester, we did spend $860 of that. The largest purchase went to the supercapacitor. For one part went to the supercapacitor at $125. We also went through 3 launch pads and then 2 microcontroller chips, which came out to the $150. The solar panel itself that we did a lot of the characteristics off of came out to the $60. Everything else was multiple iterations for small parts. So the estimated cost of the project came out to roughly $480. If we were to sell it at $1,000, that's a $520 profit, roughly. And for $1,000, or 1,000 units per unit cost came out to $280. If we sold it at $800, it would come out to the profit of $520 as well. While it doesn't seem that much lower of a price from the $1,000 units, the per cost was largely due to the capacitor, as it's a very large, or it's a very costly part. For the deployment cost, and this is more or less for the customer, for the inputs, if they had to buy their own solar panel, buy their own hydrogen fuel cell, the wind turbine, things like that. The ones that we characterized were $60 for the solar panel, for the hydrogen fuel cell, $550, and that's dry weight, it doesn't include the fuel, as well as $340 for a relatively small wind turbine. Now for a quick conformity overview, which I know is not very fun, but does need to go over. We'll have a quick document tree, document descriptions just for you guys later on, and documents that are left to be redone. So here's a quick overview of the document tree. You can see at the very top, we have the overview for the APS. We have the overview for the APS. We have our subsystems that we did go over before. There's our software, our outputs, our inputs, and for the capacitor as well. Why this is important is all of these fun numbers are mostly for documents and for later on when everyone's trying to pick this up later when they're in the next iteration. So what this goes over is just a functional design specification, which is our requirements not only from the customer but also for ourselves that we will test against, or we have test against, the test procedures so anyone who's coming after us knows where we were trying to go with the project. Bills of materials, which does the breakdown of every capacitor, every resistor, everything, so they know what they need, how much it's going to cost, and every value that they have to go through. Schematics and PCB layouts that not only go to professional fabrication when that gets done later on. But anything that they have to change, a little tweak here and there to see what else is missing. Assembly documentation for when everything goes together on one board, as well as software instructions and a zip file of all the software and the documentation for later on. It's mostly for the next iteration of the customers as well. And I'd like to invite the rest of the APS team up to go through the acknowledgements.
Okay, thank you, Dee. So the APS team would like to acknowledge Professor Kodemer, Dr. Seward. They were the main advisors for this project. We'd also like to thank Dr. Davis and Dr. Post and Jim Weber, who provided a lot of technical help on this project as well. As you might have heard, this semester was a lot of learning. We started in our prelim semester trying to tackle the entire project at once, and we spent quite a bit of this semester scoping it down towards something that we could manage in a semester. And even then, time was a constraint that was constantly present. So this was quite a challenging project. We would like to pass this on to a future detail team, and we're hoping to document as much as we can so that this project can move forward in the future and will eventually find its way up to the Artic and actually be implemented with the multispectral cameras that Dr. Seward's been researching on. And with that, I'd like to open it up to any questions.
Did your estimated costs include assembly labor?
They did not. That was pure component cost. Just dazzle you guys. That's good.
How are you planning on testing to minus 40 degrees C?
So testing to minus 40 degrees C would be accomplished when the housing had been completed and was insulated to the specifications that we've given in the housing development specification that we've written. It initially would be done in a thermal chamber very similar to the one in AXA that we use for our 0-degree temperatures. It would be initially done for similar to a thermal bakeout. It would be a thermal freeze where it would be dropped slowly down to negative 40 degrees Celsius or Fahrenheit, negative 40, it really doesn't matter. And then held for a length of time so that the entire system has reached that negative 40 temperature. I know there are that it could be held for up to from hours to days, and then once it had functionality had been established in a controlled thermal environment, the eventual goal is to do a long-term Arctic deployment where it's actually deployed in Alaska in a monitored location so that they are checking for functionality and things like that, but it is exposed to the Arctic environment and those harsh climates so that we know it will function before it is deployed on its own.
I know you don't have any more time, but if you did have one more day, it just magically appeared, what would you do next?
I think if we had one more day, I believe that a lot of us would like to spend that documenting, making sure that we have all the work that we've done written up so that the next team doesn't have to start from zero like we did, and making sure that they have a good starting point and a strong foundation to build from so that this project will go forward. And the next iteration will hopefully have a functioning, complete system that can be Arctically tested and maybe even do a field deployment with. I mean, it would be great to get more of the software working, more of the hardware, but at this point, with just one more day, I think getting that documentation really sturdy and making sure that the future team has a great starting point.
Dylan, how much help did you get from TI in making the
I had my 2,500-page technical reference manual example code, which was poorly commented and their math was wrong. And a few people who posted on forums, which were largely unhelpful. So basically the manual. No.
And I would like to mention
TI was a silent partner.
Yes, and their data sheet, for all those going into detail and later in the industry, data sheets lie.
a lot.
So much. The TI data sheet was off, which caused a lot of problems when we were trying to get a load switch that was actually active low as opposed to active high. The current output current source of the microprocessor that had the data sheet was very far off from the truth. TI did not help much at all.
And I would like,
That was really one of the lessons learned is that glossy brochures lie.
they may look nice,
Yeah,
that's about it.
Yeah.
I would like to mention Dylan is the only software engineer on the team, so the rest of us are hardware, and he was stranded all alone with all of the software, so everything that you saw was Dylan, so very big thank you for that.
Did y'all have a good time?
No. the semester, and it was a moving target that kept getting farther and farther away or wildly swinging. So once we got hardware, which happened a lot later than I would have liked, being a hardware person myself, we were able to actually start working as a team and getting the testing and the hardware and the development and the documentation all functioning together. But the first couple of weeks were definitely a learning experience of basically restarting the prelim semester and rewriting a functional design specification, reestablishing the requirements, and basically reproposing the project. So that was definitely a challenge and one of the reasons we were so short on time this semester.
Hey, no, I apologize. It was supposed to be good humored. But I guess more so what I meant is like when you're in the process of running a marathon, mile 3 hurts, mile 7 hurts. You know, none of it is a positive experience. However, when you cross that finish line, that sense of satisfaction that you have positively contributed, that you have accomplished something, that is something I feel like this whole team can speak to. So even though every day was rough and we did learn quite a lot on this project, I don't think it was necessarily the journey that satisfies us, but the fact that we can walk away from this project saying that we have learned more in our field than we have over the course of our education. We have pulled a lot from this project, so sorry about the giggles. I'm glad you enjoyed it.
It's especially nice to know that even though we haven't finished, we don't have, you know, a functional system that we can set on the counter and say, ooh, look at it work. We know that this will go forward in the future and that what we're doing today is meaningful and will be worked on in the future. So that is, you know, the finish line at the end that, you know, we have a goal to work towards.
So let's say the other team does take this up next year.
Absolutely.
What piece of advice would you give them? Let's say they email you or something. We heard you work on this. What advice do you have for us?
Optimism is a killer. We were looking at this project, we were extremely optimistic. We started very, very large. You know, we were, in prelim, all of us looked at the APS proposal, you know, no batteries, a year of operation, once a year maintenance, and went, yes, we can do this. That was a big target to tackle. So scaling it down, and even this semester, we tried to do all 3 pipelines at once, and had we spent more time on a more focused, establishing, you know, very accurate, known functionality of maybe one particular system and developing that very well. Start small, make sure it works. That would be the advice I would give. I'm not sure about the rest of the team. I know you guys all work on this too, so don't want to answer for everyone else. Anybody?
I agree with the build a little, test a little. I think that would have been really beneficial for us and for anyone progressing with this project. Taking it one step at a time would definitely be advantageous.
I know from the software perspective, as horrible as it sounds, actually reading the entire reference manual through once would actually probably have been helpful, rather than going through and trying to piece it together and continually flipping through pages, going, this is how this register works, and then saying, oh, what's the next one? I think it really would have been helpful to actually pick which peripherals or system function that I needed and have read through all of that at least once, rather than jumping straight into the code and trying to get it to work.
And same goes with the hardware, you know, but jumped on a moving train, rode it to the end, so. Any other questions? I know it's the end of the day, so.
Thank you.
Thank